CO2 is a colorless, odorless, fairly inert gas. It really doesn't react with too many things. There's a lot of different phases of CO2 that you're probably familiar with. You could have solid at low temperature, you could have liquid and vapor, and then the fancy one is supercritical. And what's amazing about supercritical is that if you heat CO2 up, just heat it up to about 88 degrees or warmer, and it makes this almost magical transition from a vapor at low pressures. Then if you keep on compressing it and keep on compressing it, and you could push it together and make it form a much higher density, liquid-like phase. And you never have a phase transition. Ethane actually has a very similar critical temperature to carbon dioxide. So you could have supercritical ethane at about the same conditions as supercritical CO2. But the big difference is carbon dioxide is not flammable. And that's really important for the workers who are working around a processing plant that has a lot of high pressure fluid. So what's really nice about carbon dioxide, it's colorless, it's odorless, it's not flammable, and it has this pressure adjustable solvent strength that goes with it. Another compound that carbon dioxide can be contrasted with for supercritical fluid extraction is butane. Now, you probably are familiar with butane a little bit, especially if you or someone in your family smokes or denies that they're smoking, but you know that they do. They have small cigarette lighters, and oftentimes they're transparent, and you can see a little liquid. That's butane. And they pick it because it has a relatively low vapor pressure, but it's enough vapor pressure so when you push the little vent on the cigarette lighter, it flows out, and you could spark it and make a flame. So there's the first contrast, right? The butane is flammable, the carbon dioxide is not. Secondly, the butane has a much higher critical temperature. So you have to heat it to much higher temperatures than carbon dioxide to make it supercritical. Third, butane is a hydrocarbon. Carbons and hydrogens, does not have any oxygen in it. It's completely nonpolar. But carbon dioxide is advantageous if you're going for molecules that might have a slightly polar character to them. When the supercritical CO2 enters the vessel, it will rapidly, almost instantly fill all the little voids. There's no liquid-vapor interface that might prevent it from traveling into the tiniest pores where the targeted molecule is residing. Secondly, it has an extremely low viscosity. It's about 10 or 20 times less viscous than water. And that's really good because it makes it very easy for the CO2 mix and find that targeted molecule and extract it or draw it into the carbon dioxide phase where its concentration is very low. And that low viscosity, coupled with the lack of a liquid-vapor interface, actually makes it very easy and very quick to pull these targeted molecules out of where they're residing and into the CO2 phase, where they can be removed from the reactor and then captured again by lowering the pressure and watching that targeted molecule fall out.